apologies for starting a bit late.
I can't believe you forgot us also.
It was because the room wasn't available. Now, what is a group?
Social organization.
No, what's your idea of a group?
Sorry.
I'm a bit sultry, that seems.
No, well, yeah, okay. If that's your idea of a group, then you're doomed. You have to have, you need to have some sort of idea of what it means to be a group, or what it does to
Are
be
we
a group.
talking strictly mathematically here?
Well, yeah, strictly mathematically, yeah. I mean,
Okay.
but what is it? I mean, like in maths, so going back to fundamentals, right? Killian told you, A is the limit of a sequence if for every epsilon there exists n or something, So that's the definition for it. But when you read it, it doesn't mean anything to you, does it? But you have the idea of a convergent sequence to a limit, which is that, yeah, as you go on, the numbers are getting closer and closer to this one point, and then. So that's the idea of a limit. Right? So what is the idea of a group?
Categorize things. Yes.
Do you have an example of a group?
Symmetries.
That's a good example.
Yeah.
Yes?
Integers?
Integers. What integers?
Like 1, 2.
All of them?
I mean, I love 0.
Okay, all integers? Says Fran.
Yeah, maybe that's like
Under a certain operation.
Yeah, you have to say what the operation is as well. Just say integers.
Addition.
addition.
Okay. That's a bad example of a group. I mean, it's a good example of a group because it's simple, but because it's useful to think of a group as of something that does something. It's some kind of transformation operation. The element of a group is like something that does something. So when you say integers, okay, don't just think of an integer as an element of the group as like a number that just sits there and does nothing. But one way to think about it is it's like an operation that shifts all integers or shifts something. Okay. So for example, if you think of 3 as the element of the additive group of integers, okay? So think of like you have on 3. These are the integers. Okay. So 3. Well, I don't know. Well, 3. Okay. So 3.
Yeah.
Yes.
Be able to stop that light on the
No,
pointing at our faces.
Which?
In front of
not
in front of
Oh, this.
the light itself is
Oh.
hanging on us.
Yeah. Sorry.
Yeah, thank you.
I didn't notice.
I did say that.
Yeah.
Sorry about that.
Oh, that's
Okay, so think of 3 as something that like moves this. Okay, so 3 does what it does. What does it do? 0 goes to 0 will be like 3, and 1 will be 4, and so it's like, and -1 will go to 2, and it's like shifts this whole thing. Yeah. So, okay. And when you do 3, it shifts it that way. When you do -3, it shifts it back where it was. That's the purpose of an inverse. It undoes what you've just done. And the purpose of the identity is that it does nothing. It doesn't change anything. So if you add 0 to everything, everything just stays where it is. Any other group that you have? So for example, you had this like Z4. Okay, so this is with addition. So this was 0, 1, 2, and 3 with addition modulo 4. Did you do this with Killian?
Yes.
Yes.
Excellent. So there are many ways you can think about this. So one of them is you have a square. and you number its corners there, 0, 1, 2, 3. Okay? And when you do 0 on it, it just stays where it is. Okay? When you do 1 on it, and it kind of rotates like this. So 0, if you add 1, it goes to 1. 1, if you add 1, goes to 2. 2, if you add 1, goes to 3. 3 goes to 0. 1 is like rotating it by 90 degrees. 2 is like rotating it by 180 degrees. 3 is like rotating it by 270 degrees. And so on. So again, there are inverses because you can rotate back. And that's the idea of a group. And so whatever you think a group is, try to think of the elements of a group that as some kind of operations. It's very useful. What is interesting about these two groups is that no, they're not the same. You have two buttons, desk control, but only the one going downwards works. Okay, now what is interesting about these two groups is that each of them you can get all the elements by taking one of them and repeating it forever, and it's inverse. Well, not forever, but like anything you want, you get by just doing one thing. So okay, so here if you look at the shift by 1, and its inverse shift back by 1, you can get shift by any integer by repeating shift by 1 a certain number of times. Okay, so that there's like one element which gives you all the shifts. Or if you took 2, that doesn't give you all the elements. It only gives you shifts by an even number of notches. Okay. And here, similarly, if you take just one rotation by 90 degrees and rotation by 90 degrees back, you can also, by doing it twice, you get the remaining one as well. Whereas if you only took the one where it rotates like this, then you don't get them all. So some elements, sometimes, in some groups, some elements give you the whole group. And this is what cyclic groups are about, which is chapter 4. Okay, so a cyclic group is going to be one which you can get by doing one of the elements there and back and getting everything. So now you know what we're doing this week. So the book. We're doing chapter 4. So firstly, so the first step on the way, we sort of have this kind of idea that what we want is to get a better idea of what these groups are like, which you can generate, as it's called, by just one element. So firstly, we need to establish that when we actually do keep repeating one element over and over again, we get a group. And that's called theorem 4.3 in the book. So, okay, so the setup is that if G is a group, and A is its element, then, and this is important because I'm introducing a new notation, so A in angle brackets. This is defined as A to the K, so K in Z. So this is a subgroup. Of G, and it is the smallest subgroup. Of G that contains A. How do you know that something is a theorem?
Because you tell us.
Yeah, because it comes in a box. That's the secondary school idea of a theorem, is if it comes in a box, it's a theorem. These aren't in boxes. There's something wrong with the book. So until tomorrow's lecture, your task is to put all theorems into boxes in your copy.
They are in italics, so I think that counts.
But grown-up mathematicians know that a theorem is something that has a proof.
I'm not a grown mathematician. No.
Shall I be worried about Daniela?
It's fine.
Shall we send her home?
We're gonna take her. It's fine.
Okay, I trust you.
We've been trying all day.
So how does one prove that something is a group?
How does one prove that something is?
That something is a subgroup of G.
It's a group within itself.
Within
The
G,
same
yeah.
operation.
Yes. So to prove, so G is a subgroup. Okay, what does it mean? So first you have to say that that A is a subset of G. So anything I can generate by taking A to a certain power is still in the group G. Well, this is obvious because we know that G is closed under the operation. So if I take one element and just keep multiplying it with itself and take it inverse and keep multiplying it with itself, I'm still getting elements of the group. So there's not, I can't jump out. Okay, so it is a subset, but we need to establish that it's a subgroup, and for this we have a test which is called proposition 331, apparently. But if you don't remember it, you have to show two things according to this proposition. And the first thing is that it's not empty. Okay, here's one. And the second thing is that whenever that it's closed, so whenever G and H are generated by A, then also their product is also generated by A, so a power of A. Okay. So this is because A belongs there. So A belongs there, that means that it's not empty. There's at least one element. And this, why is this? Well, this is because so what does it mean for G to be in the bracketed A? By looking at the definition. G is what? Yes, exactly. So G is some form of A to the K for some K. So there exists an integer K, which if I take A K times and terms it together, could be a negative K. I get G. And H being in A means that it's A to the L or some other, some potentially different. That is true. Oh no, Miriam's here, so I need to use the eraser tablet.
Oh, that's it.
H is A to the L. Well then, what is G times H? Is A to the K times A to the L, which is A to the K plus L, which is also there. Fair enough. You don't understand irony, so with me you have to be careful. Saying things like "how exciting." Okay, next. What else is there to prove? So we've covered is a subgroup, semicolon. Now after the semicolon, we should say that it's the smallest subgroup that contains A. What does that even mean, to be the smallest subgroup?
Say that louder. It's the least elements. Right.
So being the smallest subgroup, well, smallest means that everything else is bigger. Right? So this means that whenever H is a subgroup of G and A is an element of H, then H is bigger. So G is a subset of H. Actually, a subgroup. But... Okay. Well, I'm allowing G to be equal to H, but that's because, yeah. So whenever I take a subgroup of G, which contains A, it's either G or bigger. It can't be smaller. That will mean that, oh. What did I mean to write there? This one is supposed to be the smallest one. Sorry. Okay, so the bracket today is the smallest one. So how does this go? So suppose we have such a subgroup, then of course A to the K is also in that subgroup for K bigger than 0, because if A is there, then and H must be closed under the operation, then also A times A is there. So A squared is there. And A squared times A is also there, which is A cubed. And A to the 4th is also there because A cubed is there. So this is by induction. Okay. Have I lost you now?
These brackets.
Yes.
What are we actually meaning by?
These brackets, we're
Is
meaning
that
that.
just the group?
We're meaning this.
Yeah. But because that's used to being a generator of a group.
What's used to be a generator?
Like
I haven't said the word generator yet.
Yeah, but we've done it before, yeah. So
When?
like we did it in first year, didn't we?
I think she's like,
We've definitely I know what a generator is. So we're not using that in this though to be generators, are we?
Yeah, we do, but you're ahead of me.
It was just in first year we did a tiny bit on it.
Yeah. Yeah, we're getting there. I mean, now we're doing it properly. So
Yeah, it's just
yes, this thing in 2 minutes is going to be called a subgroup generated by this. If we can get there ever.
No, but it's confusing me then if it's the smallest, because if it generates the group, then surely it's the same size as the group.
What is?
The group on Cyclic.
No. I mean, it doesn't. It's not always. I just said it. It doesn't have to be the whole group. We just had the example where it's not the whole group. Sometimes it is, and sometimes it isn't.
But we're saying it's the it's the smallest that contains A.
Yeah.
Yeah, I know. It's okay.
So among all of them that contain A, this one is the smallest. You can't get any smaller than that. Okay, and I've just so it has a to the k for all positive k. If it's a subgroup, it has a to the 0 for 0 because it has to have the identity as it's a subgroup, and it has to have this because it is a subgroup, and so it has to have also, and therefore also has again by induction like before. Okay. We agreed on what this is. Okay. So when so it's a bit like what we did with okay, example. Let's take Z with addition. Okay, we just had it. So it's the integers with addition, 0 is the identity. So if I just take, what does 0 generate? Well, this is 0 plus 0 plus 0 plus 0. No matter what you do, is you get this as a subgroup. Okay, you're always only getting 0. All right. If you look at 1, so I just said, if you do 1 and minus 1 and keep adding it, you get the whole thing. No matter which integer you want, you get it by adding 1 sufficient number of times, or minus 1. Okay? But if I take 2, what do I get? All the even integers, exactly. So I'm going to call it 2z. Simple. If I do the other example that we just had, this one, again, 0, I only get 0. 1 or 3, I get everything. And 2, I get 0 and 2 only. I can't get 1 by adding 2 to itself. Okay. Pardon? Which one?
0 and 2.
Why do we get 0 and 2? Well, we get, okay, so because this is the additive notation, so instead of doing 2 to the k, we're doing k times 2, really. And k can be any integer. So if I do 0 times 2, I get 0. If I do 1 times 2, I get 2. And then I keep adding. So if I add 2 to 2, I get 4, but 4 modulo 4 is 0. And so whatever I do next is I'm only always getting 0, 0, 2, 0, 2, 0, 2. That's it. Okay?
And 1 and 3.
And 1 and 3, I get everything. So 1 plus 1 is 2, plus 1 is 3, plus 1 is 0, plus 1 is 1. And 3 plus 3 is 2, plus 3 is 1, plus 3 is 0, plus 3 is like that, modulo 4. Okay? Or if you think about it as in terms of acting on the square. Yeah? So 1 is rotate the square by 90 degrees. And 2 is rotated by 180 degrees. So if you rotate it by 180 degrees and 180 degrees, you're only ever getting 180, 0, 180, 0. Whereas if you're doing the 3 one, it's like rotating it back by 90 degrees. So the 3 gives you 1 back, 2 back, 3 back, 1 where I started. Okay? Good. Next. Now listen.
I'm listening.
Good. A is called the cyclic group generated by A. G is a cyclic group if it is generated by some element of it. Not necessarily any element, but there is one that generates it. That's called a cyclic group. Does it remind you of your first year? Killian.
Well, we did that last year as well in modular thingy.
So you're basically saying me that I'm telling me that I'm useless here.
I don't remember first year or last year. So
Good.
I'm useless to me.
I don't remember all of it.
So in this case, there A is a generator of G. So if you get an exercise, find all the generators of Z8. Okay, easy exercise. And for any, so if you get a group and any element of the group, the order of A is the smallest positive integer n, such that when you do A n times, you get the identity. Okay, remark, note. Now we have two different orders. Exactly. So now, you know from Killian that there's something called the order of a group, which means, remember? The number of elements the group has, exactly. And now there's something else which is called the order of an element. How terribly confusing.
Yeah, I hate maths.
It doesn't take much for you to start hating math.
I don't know what.
Okay. Now they can easily be reconciled because the order of A is equal to the order of A.
What?
The order of the generator is the same as the order.
Oh, right.
The order of A is equal to the order of A.
When you say it like that.
Right, I have to have some fun.
No, you don't.
Okay.
We do them tomorrow.
Hmm?
We do them tomorrow.
You can do fun every day.
No, that's enough. Let's be serious and quiet.
Okay.
No, if it's any one it's the same.
So if it's a generator, then the order of it is equal to the order of the whole group.
That's what you just said. Other ones.
Well, if it's finite. And sometimes, like, yeah, whatever. If it's not, sometimes it's not finite. Like, if it, so like, there's no order. So if you take 1 in the integers and you keep repeating it, then you don't ever get back to identity. You get 1, 2, 3, 4, 5, 6, forever, and you never get back to 0. So it doesn't have an order. But that's okay. Kieran. An easy one. Yes.
I'm reading.
Every cyclic group is abelian. It has to come in a box, otherwise it doesn't count. Okay, let's prove that G is abelian if G is cyclic. If G is cyclic, then what? What's the definition of a cyclic group?
Generated by one of its elements.
Yes, so G is A in brackets for one of its elements, this one. Then if G and H are in G, we're trying to prove that if I do G times H and H times G, I always get the same in both cases. Okay, but if G and H are elements of the group, then because G is just A added to itself, well, multiply it with itself, this means that G is A to the K and H is A to the L for some K and L integers. And then if I do G times H, what do I get? Well, A to the K times A to the L, which is A to the K plus L, which is A to the L plus K, which is A to the L times A to the K, which is H times G. End of proof.
Yeah, where they don't take working into my page.
Good. How much time is left? Oh, lots of time. So I have to go to the business school very soon. Yeah. Yeah.
There she is.
Yeah. Yeah. No, they're quite smart this year.
That sounds like a funny story.
Yeah.
It just doesn't fall for last year's and second
Yeah.
year. The year before.
Comes like in steps of 2.
See, that's something like both complimenting and offensive to me.
Oh yeah.
Because I was in 2 first years.
Yeah, but you knew what to wait for. Every subgroup.
They were all fixed, apparently.
You made the decision.
I didn't.
You made the decision.
I didn't make the decision. I had no choice.
To do the second one.
Every subgroup of a cyclic group is cyclic.
Yes.
That's a hard proof. It's a long one. It's not going to fit in the remaining 8 minutes. So an example. So example. Back to the examples we had. Okay. So examples. You don't have so many. Like you don't have so many. You don't have so many different cyclic groups. Okay, and we're gonna.
No, I think I'm going to come to you guys. Yeah.
We don't have so many cyclic groups. So basically we've seen them all.
We've seen it what?
We've seen them all.
All the cyclic groups.
Yes. So
How do we know? Surely that's not something we can know. There might be some cyclic groups that haven't yet been.
Well, it depends because we're talking finite groups.
no, we've seen the infinite ones as well.
Yeah.
Oh yeah.
Why are they called cyclic? Because the finite ones is like cycles. Yeah, 0, 1, 2, 3, 4. Now we know that they're all abelian. Okay, so what can they really be? I mean, they have to be generated by something, and so they're all like that. So I mean, not many examples. They're just different incarnations of the same group. So when I said, when we looked at the square and all the rotations of a square. This is isomorphic to Z4.
So rotation. Yeah. And then.
Now it is.
So are all rotations cyclic groups?
What do you mean all rotations?
Oh, but then symmetry also involves reflect.
Yeah.
Yeah, but then
If they are rotations of a regular polygon by
Well, let's move a vertex to a vertex. Yes, but so if you take all rotations of the plane, okay, that's not a cyclic grouping. It's not generated by a similar. A non-example. All rotations if you fix the origin and then you look all the rotations of the whole plane. Okay, so every point is rotated by the same angle.
Yeah.
And that's not a cyclic group, because how could it be a cyclic group? What is the basic one first rotation? There isn't one. You can always. What do I mean? All rotations of the plane about the origin.
Yeah.
That's a group, yeah, with composition. Okay, so one element of the group is you look at. So this is your R squared, a plane. This is the origin, and every point, wherever you get the point, and I'll give you rotation by an angle of alpha. You just do alpha like this, and it goes in a circle, and there it lands. Yeah? This is a rotation by alpha. I take all possible angles alpha, all possible rotations. That's a group, because if you do one rotation and a second one, it's still a rotation. Rotating by minus alpha is the inverse. Rotating by 0 is the identity. Okay, so it's a group. Agreed?
Yeah.
Well, it's not cyclic. It does make sense to me. Yeah, it's not, because there is no like alpha which you could use to generate them all.
Oh yeah, I get you. Yeah, I get you.
Make sense?
Because it's that if you had the rule that the alphas were like integers, like
Yeah.
like
Yeah.
If you did like all multiples of whatever alpha, that would be a cyclic group, but you wouldn't get all of it.
Okay, yeah, I'm with you.
You can only ever get countably many. So when you keep rotating something where there are finitely many options, or even if there are infinitely many, so like you could say, I'm rotating it by angle of E degrees. Okay, if you rotate by E degrees, you get infinitely many rotations. but you never get back to zero because E is what, an irrational number or something. So if you keep adding E to itself, you know, and doing it modulo 360, you can never get back to zero.
And is that what we mean by that outcome?
Alpha is any alpha. So, so what is a rotation in the plane? It's a mapping, right? For every point is moved to some other point. And every rotation is distinguished by giving the angle of the rotation. So if I give you an angle, alpha, you know what the rotation does. It moves everything by alpha. And if I give you a different angle, it's a different rotation. If I give you two like this, and you do one and then the other, you get a rotation, and it's just the sum of these two alphas. So you get a group, just compose this. Any more confusion to?
I've got a lot of confusion, but not about this.
Okay. Well, maybe then we'll leave it for later. Okay. So tomorrow we're going to finish these cyclic groups. There isn't much to do. You can read ahead.